Hello everybody, welcome to the Ultimate Physics channel. The topic of this video is applications of relativistic Doppler effect. What is Doppler effect? Doppler effect is the change in frequency and wavelength of a wave due to the relative motion between the source and the observer. We have posted two separate videos on Doppler effect, in which we have derived the expressions for Doppler effect, for the transverse case, for the longitudinal case, and finally for the general case where the angle between the line connecting the source and the observer is any arbitrary angle. So please do check out those two videos if you haven't already, to understand more about the basics of Doppler effect. But this video concerns itself only with the applications of relativistic Doppler effect. Particularly, the applications can be broadly categorized into three categories, namely applications in astronomy, applications in radar, and applications in laser cooling. In that, specifically, we will be discussing what is called Doppler cooling. So we know that there are a lot of applications for Doppler effect. In this video, we are going to deal only with applications falling under these three categories, because these three categories broadly define a vast majority of those applications of relativistic Doppler effect. So let us proceed to discuss each one of these applications in some detail. Let us proceed to discuss applications in astronomy. The first application is velocity of stars and galaxies. The Doppler effect helps us to understand whether a star or a galaxy is moving towards us or away from us. That is, the speed of approach or recession of certain stars and galaxies can be easily found out using the Doppler shift in the spectrum of such stars and galaxies. So if the shift is towards the blue end of the spectrum, that is blue shifted, then one would say that the particular star or galaxy is approaching us. That is, the frequency of the particular object is measured as greater than the actual frequency of that source. On the other hand, if it is redshifted, we can understand that the particular star or galaxy is moving away from us. So that is a very fundamental observation in astronomy, where Doppler effect comes in handy. Next, the Doppler effect is used in the detection of exoplanets. In fact, it is one of the indirect methods by which presence of an exoplanet in a distant stellar system can be detected. So, typically in a distant star, if this is a distant star, let us say, there is a center of mass for a system if there is an exoplanet circling around it. So in that case, this common center of mass about which both the star as well as the planet would go around. So under that condition, the spectrum of the star as seen by from the Earth, that would undergo a periodic change. That is, its velocity would change periodically over time. So if we plot time versus velocity for that particular star, one would have a sinusoidal function. And this is a signature of the presence of an exoplanet. Because of the tidal effects between the star and the planet, the star would also go around this center of mass. It would be that was changing its position very feebly, but still that could be detected using this signature, where its velocity, that is, the Doppler shift itself is periodic, because velocity is periodic. That indicates that the Doppler shift itself is periodic with respect to time. So this is another important application for Doppler effect in astronomy. The third one is rotation speed and sense of rotation of several astronomical objects can be detected using Doppler effect. For example, Venus. The case of Venus is very interesting because it is one of the two planets in the solar system to have a retrograde rotation. So Uranus and Venus, both of these planets have rotation in the anti-clockwise sense compared to all the other planets which have a clockwise sense of rotation about their own axis. So in that case, rotation of Venus can be detected using Doppler effect. So suppose this is Venus, and let's assume that it is rotating in this sense, that is counterclockwise about its own axis. So in that case, if you take spectrum from one edge of the Venus as seen from the Earth, the Earth that is moving towards the Earth, that would be blue shifted, that is its frequency would be higher than the actual frequency of the reference lines in the spectrum. For example, you can measure for any particular element present in the spectrum, and its spectral lines would be blue shifted, that is it would have higher frequency. On the other hand, if you take a spectrum from this particular edge, then this also would be red shifted with respect to your reference the spectral line. So one would understand that if this end is coming towards us and if it is blue shifted, this end is coming towards us, and if it is red shifted, then that end is going towards the other side. That means the rotation is in this sense, that is anti-clockwise with respect to us, right? That is how one can understand the rotation. As well, of course, from the way it is shifting, one can measure the speed, and of course, obviously, as I mentioned, the sense of rotation is whether it is anti-clockwise or clockwise. This information, for example, for Venus can be obtained from by using Doppler effect. Of course, there are other ways in which this can be done. In fact, even using radars, this can be easily detected. The sense of rotation and the speed of rotation one can do, right? And then finally, one could list configuration of binary stars, which is one of the very important applications of Doppler effect in astronomy. In fact, the relativistic Doppler effect, that is the Doppler effect in light, was first understood only because of the observation of such a shift in the spectrum of binary stars. So binary stars, we have posted a separate video titled Doppler effect in binary stars. So please do check out that video for a complete understanding of what is happening actually here. But binary stars, typically in the simplest sense, is again a two-star system orbiting about a common center of mass. So if we have two stars going around each other, for example, in one of the configurations, then again we can say that star A and star B, let us say, one star would be going away and its slide would be shifting with respect to us towards the red end of the spectrum, whereas the star which is approaching us, its spectrum would be shifted towards the blue end of the spectrum. And then of course from Earth, these two stars are too close to resolve spectroscopically, whereas if you take a spectrum from one edge and the other edge, you would see the blue shifting and red shifting, and thereby understand that it is definitely two stars going around each other. So that is another important application in astronomy for Doppler effect. Let us now proceed to discuss application of relativistic Doppler effect in radar systems. Okay, let us proceed to discuss applications of Doppler effect in radar. So there are several applications under the category of radar systems, applications in radar systems. We're listing only a few of them. The first one is overspeeding of vehicles. For example, traffic police can use a radar gun to point at a vehicle, and the reflected ray can be looked for Doppler shift. So that reflected ray is called as an echo, and so the gun fires a wave, and then the reflected wave can be analyzed for a shift, Doppler shift, and that would indicate the velocity of this object and how fast it is speeding. So whether it is overspeeding or not, whether a ticket should be issued or not, can be decided based on that simple radar gun. It's a very popular application of Doppler effect in radars. Then meteorology, there is weather forecasting, where for example a precipitation, whether it is moving, how fast it is moving, which direction it is moving, this can be analyzed using Doppler effect. So this is particularly called as Doppler weather radar. In fact, even cyclonic storms, tornadoes, these things can be, the velocity measurements can be made using Doppler techniques. Then metrology. Metrology is the science of accurate measurements. For example, motion of an object, vibration, whether it's vibrating, the scale of vibration could be very small. Doppler effect can be used for that to produce accurate measurements. And then flow for fluids. Then also one can use Doppler techniques. Flow of liquids, and one can use laser. So this also covers not just radar. When I say that it is radar, because it was originally developed with microwaves and radio waves, this was called radar. But now one can use laser also. So under that condition, it is called LIDAR. So in several of these applications, one could also use visible light, that is laser light. Need not be just visible. Any laser light can be used to do all these measurements, carry out all these applications. Then in military, a lot of applications are there. Detection of missile from an enemy aircraft, detection of the aircraft itself which is trying to hide, and then ships, warships and other kind of ships, one can detect using Doppler signal or Doppler shift. Again, space applications, plenty of space applications are there, particularly motion of satellites. One can track motion of satellites using radar signals. Shift in the radar signal indicates the velocity of the satellite. Spacecrafts one can detect using Doppler shifts. So these are some of the applications that can be listed under the category of applications of Doppler effect in radar systems. Next, another interesting application is application of Doppler effect in laser cooling. Particularly, there is a technique called Doppler cooling. We'll discuss that now. Okay, our final application is application of Doppler effect in laser cooling. Laser cooling involves a lot of different techniques, such as, for example, Sisyphus cooling, evaporative cooling, and so on and so forth. Among the different stages, there is a particular stage where it is specifically called as Doppler cooling, because Doppler shift, the idea of Doppler shift is used here. So that particular technique involves Doppler effect. So typically, a system of atoms behaves very differently at low temperatures. By low temperatures here, we mean ultra cold temperatures. So the idea that laser can be used to cool atoms rather than heating them up is very interesting because of Doppler effect. So you have a system of atoms, gas atoms, and then you strike these atoms along their path using a laser beam. Now the atoms would typically see the frequency of this laser beam to be higher than its frequency because of Doppler shift. Because it is traveling in the direction opposite to the beam, so there is going to be a shift in the frequency as seen by the atom. So from the atomic, from the frame of reference of the atoms, the actual frequency of laser is going to be less than the frequency seen by these atoms, and that is due to Doppler shift. So we have to detune the laser to a lower frequency so that the frequency of laser beam exactly matches with the spacing between the atomic levels in this atomic system. Therefore, that would ensure that the atoms get excited and de-excited. In the process, eventually, the atoms would cool. Now the question is, they absorb energy from the photons of the laser beam. One would typically think that maybe the atoms could heat up, but that is not the case here, because the atoms absorb a photon in a particular direction, and then the re-emission of the photon by the atoms after some time, that is spontaneous. And for such a spontaneous emission, effectively the momentum of the atom in this particular direction is reduced. So if the photon has an energy h nu and momentum is hk, or rather h cut k, which is reduced Planck constant, then the velocity of the atoms would be shifted in this particular direction by this much. that is h cut k over m. This is momentum over mass, and that is velocity by which, how much velocity by which these atoms, original velocity in this direction is shifted, that is towards the other side, and that means the velocity direction is this direction now for the atoms because of the shift. That means the atoms would over time slow down. I mean, it's a very simplistic explanation of what is actually happening, but then it is sufficient to understand for the purpose of this video that the laser beam in fact would cool down the atoms over time. This has a lot of applications in atomic clocks and Bose-Einstein condensates. So that completes our video on applications of relativistic Doppler effect. Thank you.